Hey, here we go again for the flipped classroom for AP Calc. Today we're going to talk about section 5.1, the first part, volumes by slicing and rotation about an axis. Um, okay, take a minute and look at this picture. What we have is I've got, let's think of this as maybe a loaf of bread. It looks a little funny loaf of bread, but we have a vertical plane here. Okay, see the vertical plane, and it's perpendicular to the x-axis, and we're slicing this loaf of bread. Okay, the cross-section is kind of triangular. If we could find the area of this cross-section, we would call it A of x. Okay, if we really wanted to find the volume of this solid, or our loaf of bread, what we could do is just sum up the individual volumes of each slice of bread, okay, which would be A of x times our delta x, from A to B, add them together, and that would be the volume. So this, well, the text here says, imagine if we slice the figure with a vertical plane, there it is, perpendicular to the x-axis, whose area is represented by A of x. The volume of that slice would be A of x times delta x, the thickness of the piece of bread, and the volume can be approximated by the sum of all the A of x's times delta x's, which is looking fairly close to a Riemann sum. In fact, if we take this volume and we have infinite number of subintervals, and we can define that summation as the definite integral from A to B of A of x dx, as long as we have that infinite number of subintervals. The next slide will show you a sample problem. Okay, here I've got a right circular cone. Its base is on the y-axis, centered at the origin. The height of the cone, as you can see, is 6. The radius of the base is 3. This upper edge of the cone, where I'm moving the mouse right now, is actually a straight line, and we could define that upper edge, since we know 2 points, 6, 0, and 0, 3. We can find the equation of that line to be 3 minus x squared. So what we want to do is, how would you calculate the volume of this cone? Now, I know there's a geometric formula for the volume of a cone, but let's see if we can do it with integrals. First thing, sketch the solid. We did this. Find A of x. Well, A of x is going to be circular here, okay? So A of x is going to be of the form pi r squared. Our only job is to determine what the radius is. Well, as you can see, if this is the center line, the radius is always going to be whatever the y value of the function is, or namely 3 minus x over 2. Okay? That's true here at 3, and that would be true way down here at 0, because if I put 6 in for x, do I not get the radius of 0? Okay? So what we need to do is we're going to square that radius, because pi r squared, calculate the integral of A of x dx, so that would be the volume would be the integral from 6 to 0 of pi times 3 minus x over 2, that's our radius, squared. And when we do that and evaluate it at 6, 0, we get 18 pi. Okay? Amazingly enough, the formula for the volume of a right circular cone is 1/3 pi r squared h. So if you take 1/3 pi times 3 squared times 6, I believe you will get 18 pi. How about the volume of a pyramid? Let's say this pyramid has a height of 3 meters, 3 centimeters, it doesn't matter, and a square base of 3 meters by 3 meters. Okay, first thing we got to do is determine, we've sketched it, first thing we got to do is determine what the cross-sectional area is. The base is square, so the cross-sectional area will be a square, and if it's at 3, we could say it's 3 by 3, or x, because this point here would be 0, and if the height is 3, this would be the points 3, 0 right here. Okay, so the cross-sectional area would be x squared. To find the volume, I'm going to take the integral of that from 0 to 3. Notice this is not a circle. I'm just summing these rectangles, or squares up, times x squared. When I do that, I get x cubed over 3, evaluated at 3, 0, 27 over 3, or 9 meters cubed. Okay? Pretty simple. How about if we want to find a solid of revolution that has a circular cross-section? For these type of problems, A of x, because that's the area of the cross-section, would be pi times the radius squared, which is pi, And we're going to define that radius in terms of x, so some function r of x squared. Step 1, draw the region and identify what r of x is. And you should identify the upper and lower bounds of your integration. Square r of x, why? Because pi r squared is the area, and multiply by pi. This will be the area of the cross section. When we integrate it, we're basically adding up all the volumes of those individual cylinders, if you will, to find the total volume. Here's a sample problem. Our function is square root of x, denoted by the blue line, okay? And we're going from 0 to the line x equals 2, okay? So the problem is to find the volume of a solid created when this region bounded by f of x equals 0, okay? X equals 0 probably doesn't even need to be in there because that's the y-axis and the curve actually meets at the origin. X equals 2, however, it does need to be in there, and the x-axis. So these are the boundaries of this region, which we're going to revolve. We're going to revolve that around the x-axis. Okay? So first of all, let's determine what our radius is. Will not the radius be whatever the height of this rectangle is, because this rectangle is revolving. It will come out of the screen and go around the x-axis. So the radius will be the square root of x. The limits of integration, well, the limits of integration here will simply be 0 to 2. Okay? So to find this volume, I'm going to integrate pi r squared, okay, or pi r of x squared from 0 to 2. Okay, don't forget we got to square that square root of x. That becomes x. And when I do that, I get the volume is 2 pi. Okay, pretty cool. All right, this one's a little trickier. Instead of going about a horizontal axis like the x-axis, we're actually going to go about a vertical axis. So our problem is to find the volume of the solid produced when the region bounded by x equals 8, dashed line x equals 8, and x equals y squared plus 1. That is this parabolic shape here, the red line, okay, is revolved about the line x equals 8. So I'm going to revolve it around this line right here, which is a vertical rotation. Okay, may seem difficult, but it's not. Okay, the first thing we need to do is find out what r of y. Notice that now our variable is y because everything is with respect to the y-axis. Okay, well, r of y is 8 minus y squared plus 1. Let me show you how we got that. If I'm just taking this whole rectangle and I revolve it around the line x equals 8, then wouldn't the radius be 8? That would be the blue plus the yellow rectangle, okay? So that's what I start out with. What I really want is this blue rectangle. What do I need to subtract from 8 to get that blue rectangle? Well, I need to subtract this little yellow rectangle. And believe it or not, that is the function value of x equals y squared plus 1. So again, yellow plus blue equals 8. I'm going to subtract the yellow, y squared plus 1, and that will give me the blue. That comes out to be 8 minus y squared plus 1, or doing some simple math, becomes to be 7 minus y squared. The next thing I need to do is to find the upper and lower bounds of integration. Okay? Well, the upper and lower bounds of integration are not going to be on the x-axis. They're going to be on the y-axis. So the way I do that is I need to find out, okay, where does this cross the line x equals 8? When I do that, when it crosses the line x equals 8, I say 8 has to be equal to y squared plus 1, okay, because these two lines intersect there, okay, and that happens at y equals the square root of 7. And down here, it's just going to be the negative square root of 7, okay, because it's going to be 8 has to equal this equals x squared y squared plus 1, and that can be either positive root 7 or negative root 7. So those are our upper and lower limits of integration, okay, and that's where you see this right here, okay. Again, what are we going to do? we're just going to integrate this. Whoops, I'm sorry. We're just going to integrate this pi r squared. Okay, there should be, I believe, a parentheses here after the before the 7. Okay, pi 7 minus y squared quantity squared from root 7 to negative 7. So pulling the pi to the outside, it's equal to the integral. I'm just expanding this expression, the binomial, of y to the 4th minus 14y squared plus 49. From root 7 to negative 7. And when I do integrate that, I get pi times the quantity y to the 5th over 5 minus 14y cubed over 3 plus 49y evaluated from root 7 to negative 7. When you do the math on this, it all boils down to that the volume equals 196 times the square root of 7 times pi divided by 15 units cubed. Okay? Not so bad. Time to practice. Well, this has been the first part of section 5.1. Next time, oh boy, washer solids. Those are fun. For right now, what I want you to do is to practice on pages 423 to 426, 1 through 30. Peace.